Okay. So, okay. So this is an example of such a generative classifier. Okay. So this is, called linear discriminant analysis. Linear discriminant analysis model. Okay. But you can see, even though we have a term discriminant here, but this LDA model is generative. Okay, I mean, because we just say like the regression models are the discriminating, doing discriminating to classify classes, but this is called linear discriminant analysis. So just don't be misled by the name. Okay, so you can see that here. Okay, mu. Okay, we have a prior. Sigma, we have another prior, and you can see we directly have like a setosa. Okay, equal to PM dot normal. We assume, okay, this class is in Gaussian distribution or normal distribution. Okay, and the name setosa. Mu is from mu 0. Okay, remember, I mean here, for both mu and the sigma, we have like a shape. I mean, we have more than one. Okay. Sorry. Okay. So mu is mu 0. Standard deviation is sigma, and observed. Okay, we directly get the data. Okay, to fit here, and Vescala, same thing. Okay. Mu is another one, mu 1, and then we directly get the data to fit with that. So once we have that, okay, obviously we are able to, what should I say, have the result for mu 0 and the mu 1, right, based on the data. And then the interesting thing for the LDA is that the boundary is actually a closed form. It can be directly computed from the mu 0 and the mu 1. Okay, basically just, okay, we call the boundary, okay, as a BD, and then, the boundary is assigned to be the average of mu 0 and mu 1. And then we generate 1,000 sample. Okay, so this is, different from the previous model in the sense that, you see, in all the model that we have seen normally, like you can see, we normally feed the data. For example, observe equal to ys. We feed the data. Into the result model for the last line. But here, okay, in this example, for the generative model classifier. You can see that, okay, the place we fit the model, with the data set is here. This one and this one. And then after that, we compute the boundary. Okay, so this is very, very different. Okay, very, very different. Okay, and you can also plot the figure, okay, to show these two classes. Okay, this is the important. We can still get 94% HPD, okay, out of it, okay, and it looks like this. And if you compare this one with the one we had for the regression, logistic regression model, okay, it's going to take some time to this one. You will see that the result is pretty much identical, almost. Okay, use regression, logistic regression, you get the boundary like this. If you use like LDA, obviously the idea is different, but you still get pretty much the same boundary. Okay, and you can also output the summary of this, and so that you can compare it with the boundary that you have, like in the previous logistic regression model result. Okay, you will see like they are almost identical. Okay, almost identical, pretty similar. Okay. So so this LDA works for the 2 classes and 1 feature. So it's a very limited application. It has very limited application. Because if you want to extend this model to like maybe more than 1 feature, okay, you want to model like or you want to model by like classes as multivariate Gaussians, okay. So this is like going to be obviously more features, more than 1 features, okay. Then it is possible to relax the assumption of the classes sharing the common variable covariance, okay. I mean in this LDA, if you look at the code that we were writing, okay. Here, okay. Sorry, where is it? This one, okay. Yeah, we have different mu, okay, but these 2 setosa of this color share the same sigma. Okay, this is obviously one assumption that we have for the LDA, okay. But if you want to relax this assumption, okay, such that like each class has its own like variance, okay, this leads to a model known as quadratic linear discriminant, QLD, QDA, okay. So now the decision boundary is not linear but quadratic. So it's more complicated, okay? And in general, LDA and the QDA model will work better than logistic regression when the features we are using are more or less Gaussian distributed. So if you already know, okay, this is the problem, okay, where your features are Gaussian distributed, then you probably prefer to use LDA or QDA because they will tend to give you a better result, okay? But if if you cannot be sure about the distribution of your feature, okay, then the logistic regression will perform better in the other cases, okay? So basically, it depends on the problem, okay? Which type of problem is more suitable for LDA, QDA, this type of generative classifier, which type of problem is good for like a regression type of solution. Okay, here is a very important hint for you. Okay, and one advantage of a generative model for classification is that it may be easier or more natural to incorporate prior information. Okay, so we may have information about the mean and the variance of the data to incorporate into the model, and obviously because like here, okay, when you write the model, okay, it's easier for you to incorporate like different priors, okay, to like different classes. Okay, so that's like one advantage of that. Okay, but to be honest, like the regression type of model can do that too, but it's just not as straightforward as generative classifier, okay? So it is important to know that the boundary decisions for LDA and QDA are known in closed form, and hence they are usually computed in such a way. So for example, LDA is just like the mean is just the boundary is just like the average of the mean, right? And for QDA, yeah, it's more complicated, but you can still use a quadratic form to calculate the boundary. Okay, so to use LDA for two classes and one feature, we just need to compute the mean of each distribution, average those two values, and that's it. So in the preceding model, we just did that, and with a Bayesian twist, because we are actually doing the calculation from the distribution, so we are able to also get, like, for example, 94% PDA, okay, HPD, I'm sorry, HPD, okay, so that's like, very nice, okay, so, we estimate the parameters of the two Gaussian, and then we plug those estimates into a predefined formula. So where do the formula come from? Without getting into too much detail, to obtain that formula, we must assign the data is assumed. We need to assume the data is Gaussian distributed, and hence such a formula will only work if the data does not deviate from normality too much. Okay, so this is an assumption that we have. I mean, that the data, the features are Gaussian distributed. Okay, I mean, if it's not the case, I mean, it's much more complicated. Okay, of course, we may hit a problem if we want to relax the normality assumption. Okay, can we do that? We could. Okay, such as using student t distribution if you have a lot of outliers, and you want to deal with those outliers. Remember, the way to deal with outlier is to, instead of using Gaussian, we can use student t, okay, or multivariate student t distribution. I mean, in the case if you have like multiple variables, okay, then, okay, in such a case, we can no longer use the closed form for the LDA. I mean, the result of the boundary is no longer a simple computation. Okay, it's not a closed form. Okay, or QDA. Okay. However, we can still compute a decision boundary numerically using pi MC3. Okay, but we will stop our discussion here. Okay, if you are interested in like a generative model, generative classifier, I mean, you probably want to check out the references that I have provided at the beginning of this class. Okay, there are more discussion on this type of stuff. Okay, so now, okay, the last topic, okay, for this chapter is like, sometimes we want to, predict or like to calculate or to inference, okay, a certain number, okay, which is the count data type. Okay, the count, I mean, data type is like, first it must be integer, right? If you count something, I mean, it must start from 0, right? I mean, well, I mean, the worst case is you don't count any event, then that's E0. You couldn't get a negative number, right? So this is like, how do we deal with such a prediction? Okay, using the linear model, okay, is we can use a Poisson distribution. We call such a regression Poisson regression. Okay, so this model assumes data is distributed according to Poisson distribution. Okay, so one scenario where Poisson distribution is useful is when counting things. For example, the decay of radiative nucleus. Again, this author, I have to keep reminding you the author's background because he's into like the quantum chemistry. So the example he used is not so what should I say? Not so straightforward for regular people. Okay, so this because you probably don't know the decay of a radiative nucleus is countable, right? At least I don't know that much. Okay, but the other example, okay, I think is much more friendly. Okay, for example, the number of children per couple. You can have some. I mean, your significant other can have some children. Okay, but the number of children can only be integer, and it can only be 0, 1, 2, 3, right? Obviously, okay. Or the number of Twitter followers. Okay, again, that's a simple example for the count data set. Okay, so what all these examples have in common is that we usually model them using discrete non-negative numbers, such as 0, 1, 2, 3, blah, blah, blah. So this type of variable receives the name of count data. So the previous example, for example, like regression, okay, linear regression, or multiple linear regression, deal with like predicting a value, right? That value does not have to be integer, right? Okay, for logistic regression, we are predicting or classify. We are classifying like a binary class, right? For softmax regression, we are classifying multiple multiple class classification. Okay, and but this one, the Poisson regression, I mean, deal with like we are predicting the count data type. Okay, that's important. So for the Poisson distribution, imagine we are counting the number of red cars passing through an avenue per hour. We only count the number of red cars, not the other color, just the red cars. Okay, so we could use Poisson distribution to describe this data. Okay, so what is the nature of Poisson distribution? Poisson distribution is generally used to describe the probability of a given number of events occurring on a fixed time or fixed space interval. Okay, for a given time or given space interval. Okay, if you want to describe the number of events, okay, that will occur, okay, within this fixed interval, then we normally use Poisson distribution. Okay, so the Poisson distribution assumes that events occur independently of each other and at a fixed interval of time, okay, or space. So again, this independent assumption, okay, is an important one in the Poisson distribution, and luckily in most of the applications, we could assume such a assumption. Okay, the event happen independently. Okay, but this is not necessarily the case. Okay, I mean sometimes one event will impact the occurring of the next one. Okay, this is like sometimes this assumption doesn't work. Okay, but most of the time it works well. Okay, so this discrete distribution is parameterized using only one value. Okay, which is a rate. Okay, which is normally use the lambda to represent that rate. Okay, so mu corresponds to the mean and also the variance of the distribution. So the probability mass function of Poisson distribution is given like this. And you may wonder what is the relationship between the lambda and the mu, because lambda is rate, right? And the mu is the average. Okay, so rate is normally, okay, lambda is normally 1 over mu. Okay, and but in this formula we only use mu here. Okay, and also one important thing you need to remember is that, okay, Poisson distribution is only the few distribution that the mean and the variance are the same. Okay, mean and variance are the same. Okay, both of them are represented by mu, by the way. Okay? So, here, mu is the average number of events per unit of time space. Okay, x is a positive integer value. Okay, so here x is that refer to that count data. Okay, x, a factorial of x, you know the factorial, so I don't need to explain. Okay, so this small piece of code will plot the Poisson distribution family for different value of mu for you. Okay. Here I want to remind you, I would like to remind you that Poisson distribution is not a continuous distribution. The reason we draw this looks like a continuous distribution is just to give you an idea, okay, you know, how this this distribution change over different like interval. But I mean in reality, I mean, where this distribution really take value is that integer value. So you can see, I mean, those values were like marked by the big dot. Okay, I mean the line between the big dot is just an indication of the trend, but it doesn't. It's not the indication of that. Oh, there are values in this interval. No. Because Poisson distribution is a discrete distribution. Okay? So, you can also see that, okay, because mu indicate like the average number of events for a given period of time, right? So the more, the higher the mu, okay, you know, the more likely, okay, for example, mu is, when mu is 8, okay, you can see the distribution looks like this. You have more chance to have a higher count value. And when the mu is very small, such as mu is 1.5 or mu is 0.5, you can see that, okay, the chance for mu to have like a high value is, I mean, it decreased drastically. Okay, drastically. I mean, after, I mean, you know, a few counts. Okay, and also, just want you to remember that even though I say, you know, the Poisson distribution is a discrete distribution, right? The value of mu does not need to be integer because mu is the average number of events for a given, you know, time interval, for example. And that average may not be integer. So just like what you see here, it could be 0.5, it could be 1.5. That's fine. That's fine. That's a valid value for Poisson distribution. Okay? So mu can be float. Okay? So so remember Poisson distribution is a discrete distribution. Okay? The Poisson distribution can be seen as a special case of the binomial distribution when the number of trials n is very large, but the probability of success p is very low. Okay, so without going into too much mathematical detail, we can try to clarify this statement. Okay, so following the car example, we can affirm that either we either see the red car or we do not. So we can use a binomial distribution like this. This is a probability that we see a red car. Okay. So, I mean, in this case, the mean of the binomial distribution is like, you know, this is very simple calculation, like it's n times p. And the variance, okay, you can, again, this is a simple calculus. It's going to be np times 1 minus p. But if, I mean, even if you are in very busy avenue, okay, the chance of seeing a red car compared to the total number of cars in a city is very small, right? I mean, for example, in Taiwan, I mean, for some reason, this is, by the way, a very interesting observation. I mean, if you go to a street and try to see like a different car in different colors, you will find that the cars in white, I mean, you have most of the car in white. I don't know why. Okay, I don't know why. Because I just came back from US. Yeah, I wouldn't say, I would say like the variation in color for cars in US is much more than the variation of the cars in color in Taiwan. Okay, I don't know why. I don't know why. But in Taiwan, I mean, the number one color in cars is white, and the second highest one is probably black, right? I don't know. I don't know why. I mean, everybody, but my car is also white color. Okay, I'm not saying like there's any problem with that. I mean, even for myself, I use white color. I mean, the reason I got a white car is because like the sales tell me, car sales tell me like the white color, it's easy to see if there's any if there's a dirt on the car, it's easy to see, and you can easily wipe it out. But well, you will find that, I mean, that's the majority of the color on the street. Okay, but anyway, okay. So obviously the chance of seeing a red car compared to the total number of cars in a city is very small. So in other words, okay, the N is much larger than P. Okay, number of cars is much larger than P. Okay, so in other words, N times P, okay, is roughly the same as NP times 1 minus P, right? Okay, I mean, statistically speaking, or like numerically speaking, NP and NP times 1 minus P, I mean, they are very close. They are very close. The only difference is the factor 1 minus P. But since the P is small, so these two terms are similar. So if that's the case, so you can see, you can approximate the variance by NP if the average and or mean, okay, if the mean or like expected value and the variance are both NP, then we can confidently state that our variable is distributed as a Poisson distribution. Okay, so that's why we normally consider Poisson distribution as a extension, okay, or like a special case of like a binomial distribution. Okay. So obviously we could use like a Poisson distribution to deal with like the number of car prediction, okay, on the street. Okay, so you can directly do that. Okay, but sometimes, I mean, if you do that directly, you will find that, okay, the predicted number is usually, okay, always smaller than the real value. Okay, so what should I say? It's the opposite. The predicted value is usually higher than the real value. Let me correct myself. Okay, so you have fewer zeros compared with the data. Okay, this is almost always the case when it comes to the Poisson regression. So what do we do? I mean, of course, like we haven't. I mean, we didn't see an exact example here. So I encourage you guys to really like create a simple Poisson regression and compare that with a count data set, and you will see like this phenomenon, which should convince you, okay, to to explore ways to to correct that. Okay, so what do we do? Okay, so first, I mean, let's consider what happens. I mean, why do we have that? Okay, so when counting things, one option is to not count the data a thing. That is to get a 0. Okay, so number zero can generally occur for many reasons. Okay, so we get a 0 because we were counting red cars. Okay, that and a red car did not pass through the avenue. Okay, so there's no red car. Okay, or because we missed it. Okay, either there's no red car, or we missed it. Okay, what do we mean by we missed it? Okay, maybe we did not see that tiny red car behind a large truck. Okay, the car can be blocked. Some cars can be blocked by the other cars, right? So sometimes, when you count the red cars, you miscount some events. Okay, that happens from time to time anyway. So if we use a Poisson distribution, we will notice, for example, when performing a posterior predictive check, that the model generates fewer zeros compared to the data. So when it generates fewer zeros compared to the data, it means we have too many ones. Okay, the number 1 is a little bit too high, too high. So how do we fix that? That's here. I just want you guys to understand the reason, the phenomenon, the issue. Okay, where the problem comes from. Okay, so we may try to address the exact cause of our model predicting fewer zeros than observed one. Okay, and include that factor in the model. So we can fix that, okay, directly. Okay, for example, we can incorporate like a stronger plier, okay, to fix that. That's obviously doable. Okay, that's obviously doable. But you probably need to know, for example, you missed the events, right? So what is the rate that you missed the events? Okay, you need to know a little bit better about that to design a more reasonable plier. Okay, in order to incorporate that into your model. Okay, but this is not very convenient. Okay, as is often the case, it is enough and easier for our purpose just to assume that we have a mixture of two processes. This is like one solution that is much easier, but this solution, okay, require you to mix two processes. Okay, one modeled by a Poisson distribution with probability psi. Okay, so this part, the first part, is the simple Poisson regression that I was talking about. Okay, so this part is just like what it is, like when you use a Poisson distribution to replace the logistic or like softmax. Okay, so that's easy. So with the probability psi, okay, you model, you put the part to be modeled by Poisson distribution. The other part, when given extra zeros with probability 1 minus psi. Okay, and obviously psi and 1 minus psi, they add up to be 1, right? So you consider all the cases. So you can sort of consider this second process as the process that you miscalculate a car, the red car. You miscalculate a red car. Okay, some red car that either got blocked by the other cars or you simply just missed it. Okay, and the second process deal with that. Okay, so how do we call such a model? We call it zero inflated Poisson model. Zero inflated Poisson model, and which has a very nice abbreviation called ZIP. Okay, ZIP. Zero inflated Poisson model. Okay. So in some text, you will find that psi represent the extra zeros, and 1 minus psi the probability of the Poisson. I mean, basically, it's the opposite, exactly opposite. Okay, but it doesn't matter. I mean, it's really like the choice of the programmer to do the model. Okay, so you know, this is not a big deal, obviously. I mean, just pay attention which is which for a concrete example. Okay, so basically a zip distribution is like this. Okay, so when the outcome is 0, okay, we have 1 minus psi plus, okay, because here, okay, remember maybe it's easier for us to look at this one, okay? When the outcome is not 0, okay, this is what we get, right? This is Poisson distribution function, I mean, obviously, right? No problem with that, right? Okay, so when outcome is 0, okay, I mean, for 1 minus psi, I mean, you have this missed calculation, okay? And then the other part, okay, it's going to be, you know, this probability. Why is this the probability? It is, you know, when the outcome, I mean, the outcome is non-zero, okay, but, you know, you, how should I say? I shouldn't say outcome is non-zero. The other part, okay, when you have something that you follow the Poisson distribution, and you plug in x to be 0. When you plug in x to be 0, this part becomes 1, right? When you plug in x to be 0, the factorial of 0 is 1, right? So they will leave just e to the power of minus mu, right? So this part is what came from the Poisson distribution when you have a 0 event. Okay, so but you add this 1 minus psi, okay, extra probability to it to sort of adjust that. Okay, sort of adjust that. So here, okay, 1 minus psi is the probability of extra 0. Okay, and then let's try an example. Okay, we create a few synthetic data points. Okay, so we have 100 point. Okay, the real theta is 2.5. Okay, and the psi is 0.1, and then we just randomly create some numbers, and then so the numbers looks like, well, it doesn't give you those numbers, but anyway, so this model is very simple. Okay, I mean, okay, we call it just zip. Okay, psi is like from a beta distribution with alpha and beta, A and B to be both 1. Okay, when A and B are both 1, remember it's a flat, right? If you remember the beta distribution, when A and B are both 1, I mean, it's a flat. So it's this one is a non-committal prior for psi. Okay, we just know like a psi is a value between 0 and 1, and then okay, theta, okay, is going to be, I mean, PM dot gamma, okay, we just call gamma, okay, theta 2, 0.1, okay. Here, I mean, we, this is like a prior, okay, this is a prior to that theta, okay. And the 2 and 0.1 is not a very strong one, okay, strong prior. But then, okay, what happens that, okay, after you have the theta, 2 and 0.1 is a prior, right? And after you have that theta, you put theta here. And we call the zero inflated Poisson. So this zero inflated Poisson already have the function like this. Okay, but you need to provide like a adequate like parameters. Okay, so you put the psi from here, you put theta from here. Okay, where theta has to be in a gamma distribution. Okay, sorry, gamma is a prior. Okay, gamma is a prior. Okay, so theta is just. I mean, by the way, this gamma is a very flat gamma. Okay, flat result. So I mean, you just provide the theta here and observe data. Okay, and then you just do this generate a sample. That's it. Okay, and then this is a result. Okay, of like trace file, trace result. Okay, and then okay, so it actually gives us like a pretty nice result. Okay, because you can see here. Okay, theta. Okay, because the real theta is 2.5, right? Real theta is 2.5. Real theta is 0.1. So you can see like the highest place for psi is in between 0.1 and 0.15. Okay, somewhere here, in the middle of maybe 0.12 or something like that. Okay, and for the theta, you can see, okay, it's going to be, again, it's in between 2.5 and 3.3. So it's close enough, okay? It's a close enough, estimate for the data set, okay? So just want you to understand, okay, this example, okay? So then, the zip model may look a little dull, but sometimes we need to estimate simple distribution, such as the one that we just used, okay, the example we just used, or others such as Poisson or Gaussian distribution. So anyway, we can also use Poisson or zip distributions as part of linear model. So as we saw in the logistic and softmax regressions, we can use an inverse link function to transform the result of the linear model into a variable in a range suitable to be used with other distributions than the normal. Okay, so follow the same idea, we can now perform a regression analysis where the output variable is a count variable using a Poisson or zip distribution. So this time we can use the exponential function e. Okay, the reason to use e is to to make sure it's bigger than 0. Okay, the result is larger than 0. Okay, as the inverse link function. So this, if you want to use a count, deal with count value, the inverse link function is usually e. Okay, exponential. Okay, so this choice guarantees the value returned by the linear model are always positive. That's what I said. Okay, so you can see that. Okay, alpha plus x beta is the